Welcome back to part 2 of chapter 20. We're going to quickly cover 20.5, reactions of carboxylic acids, and then we are going to cover 20.6, which will contain a lot of nomenclature for those derivatives of the carboxylic acid moiety. All right, so to wrap up just the conversation we were having about carboxylic acids, we will see a few more reactions with carboxylic acids beyond this section, but we do want to review a couple of things. The only reduction that we have that is strong enough for the carboxylic acid is the lithium aluminum hydride, LAH. You may also see it written as LiAlH4. It's the same thing, lithium aluminum hydride. And then work up with water or a dilute acid. It's important that you make these two separate steps. It's dangerous to put water in with the lithium aluminum hydride. This will reduce a carboxylic acid to a primary alcohol. You do not need to know the mechanism, but you do need to recognize that this set of reagents works for carboxylic acids, whereas something like sodium borohydride does not. So again, you do not need to know this particular mechanism. There are other ways to achieve this same reduction. For instance, with BH3, right, kind of like with hydroboration oxidation, I will not be using that. If you see it in your homework, that might be one thing, but I will not, I will never use that to reduce my carboxylic acids in my notes or in my solutions. Okay, here's the meat of this discussion, and that is our next set of functional groups. We are looking at the carboxylic acid derivative. So anything that we can add onto that carbonyl that is going to keep that oxidation state the same is going to be a carboxylic acid derivative, right? Anything that is more electronegative. So when it's carbon or hydrogen, ketones and aldehydes, that does not count. That is not going to fall in this category, but pretty much everything else will. So Z can be a halogen, it can be an O carbonyl, it can be an OR or an NH2, right? The acid halides, the anhydrides, esters, and amides are all carboxylic acid derivatives. While the nitrile looks a little bit different, it's still a carbon with 3 bonds to a more electronegative element, just like all of these. And it tends to have some similarities in how it reacts. So nitriles will be included in this chapter as well. Now, when we think about halides, esters, amides, and anhydrides, they're different levels of reactivity. Acid halides and anhydrides are not particularly stable, so you don't find them in naturally occurring compounds as much, but it does make them good starting materials for synthesis. Esters and amides, not as reactive. Unsurprisingly, you find them more in nature because they're more stable, and you have a random assortment here of some esters that occur in nature. Amides are, the amide bond is incredibly important, right? Is the backbone for the structure of proteins. You also find amides in all sorts of other natural products. Here is referenced melatonin. All right, let's get down to some naming. We're going to start with the acid halides or acyl halides. You are going to take, instead of going all the way back to like the alkane name, you are going to think about what the name would be if Z was an OH. Right? You're going to take the acetic acid name and you are going to modify it from there for the next few functional groups. All right, so for acid halides, you think about the carboxylic acid parent and you drop ic acid and you add YL halide. Now, you don't use halide. You put whatever halogen is there. So, for instance, here we have a bromine. Here we have a chlorine. So, bromide and chloride are used. Acetic acid is one of the common names that you were supposed to know. And so, acetic acid becomes acetyl bromide. You leave the O if there is an O. So, benzoic acid becomes benzoyl chloride. You don't have to worry about this. I canceled that in the last video. And let's do a practice problem before we move on to anhydrides. So let's take a few interesting functional groups. How might we handle this? All right, so if I look in here, I have a carbon chain of 1, 2, 3, 4, 5. So that's pentane. If this was a carboxylic acid, it would be pentanoic acid. So my parent becomes pentanoyl bromide. Right, I dropped the ic acid. And then I put in my substituents like I would with any other parent chain. On carbon 3, there is a bromo. And on carbon 4, there is a nitro group. This is 3-bromo, 4-nitro, pentanoyl bromide. It will always be on carbon 1 because it has to be at the end. So you don't have to put a number here. Just like with any of our other high priority functional groups, you would like the the longest continuous chain that contains that high priority functional group. Anhydrides, a little bit different here. So the anhydride, you wind up with 2 R groups, right? One on each side. And what you're going to do is you're going to look at what this carboxylic acid would be on one side. If it's symmetric, rules are a little bit different. And you're going to take that carboxylic acid parent and you're going to drop just the acid, right? So you'll keep the ic or the oic and you will add the word anhydride. Anhydride. All right, so we see over here acetic acid becomes acetic anhydride. You have that 2 carbon chain on both sides. If we had, let's see, something like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 on both sides. This would be hexanoic anhydride. Don't worry about a cyclic structure. I would not ask you for that. Not all anhydrides are symmetric. So if you have an asymmetric anhydride, you are going to name both sides and then write them down alphabetically. So over here, you have an acetic acid derivative, and on the left, benzoic acid. We're going to write them down alphabetically, acetic, benzoic, anhydride. All right, for another random example. All right, so on one side, we have 1, 2, 3, 4. So that's butanoic. And on the right, 1, 2, 3, 4, 5, 6, 7, 8, we have octanoic acid. So we're going to write this down alphabetically. We have butanoic, octanoic, anhydride. It's as simple as that. I won't put any substituents on an anhydride. That gets a little bit more complicated, but you should know how to name or draw the structure from the name of some simple symmetric and asymmetric anhydrides. All right, naming esters. This one can be a little bit tricky. You're going to have R, carbonyl, O, and then an R group. I'm going to put R1. R1 this is the pattern you're going to see. R1, there's Bree saying hello. Let's set this up. R1 is going to be an alkyl group at the beginning, and then R is going to be your parent, right? So the side that is connected to the carbonyl, that's your parent here. So how are we going to handle the parent? You are going to drop ic acid, and you are going to add ATE. All right, so over here we have acetic acid, right? It doesn't matter which way it's pointing. The carbonyl side is the parent. So 2 carbons is acetic acid. So that becomes acetate. And then the OR group, you have a 2 carbon piece. That's ethyl acetate. All right, let's put something else together here. A little benzene ring. Doesn't matter how long that chain is. You're going to have your R group, your alkyl group, 1, 2, 3, 4, 5, 6. So it's going to be hexyl. And then this comes from benzoic acid. So that becomes benzoate. All right, drop the ic acid, put ATE, hexyl benzoate. You really have to pay attention to what's connected to carbonyl versus what's connected directly to oxygen. It could be drawn in either direction. Down here where you have the carboxylic acid derivative, here we go. I would only stick with something symmetric, but you have an ethyl on both sides, so it's just diethyl. The 3-carbon dicarboxylic acid is malonic acid. It's one that you're supposed to know. So it becomes diethyl malonate. This one will be important in chapter 21. So it's something to take note of. I will not ask you to use that cyclohexane carboxylic acid. I cannot impress upon you enough, you need to practice nomenclature this week. There is a lot of new little rules, none of which are horribly difficult on their own, but there's just a bunch of them at once, so make sure you're practicing. Amides. Amides are an interesting group. So initially it's pretty easy. You're going to take that carboxylic acid derivative. Let's make that into an H. And you are going to drop ic acid. We see that a lot. And we're going to add amide. All right, so acetic acid becomes acetamide. Benzoic acid becomes benzamide. All right, something a little straightforward here. Hexanoic acid becomes hexanamide. Something to throw in, and this applies to any of the functional groups we've looked at so far. If you had a double bond, you know how to handle this, right? The parent in here would be butene instead of butane. It would be butanoic acid if it were a carboxylic acid. So this becomes a 2 because the 1 will always start at that carbonyl carbon. This becomes 2 butene amide. You could also put the 2 inside, right? But-2 amide. Now, skip over that. Now, what's interesting with amides is sometimes you're going to have R groups on the nitrogen. When it's 2 hydrogens, the rules are what we've just covered. But if there is an alkyl group on that nitrogen, we have to deal with it. We treat, let's see, if we've got a nitrogen with varying R groups here, we are going to treat these R groups as substituents. That'd be cool if I could spell. There we go. They're substituents, so they need a locant, they need a number. The number is going to be the capital letter N. That's going to tell you the location. So over here, a couple of simple examples. You have acetic acid parent, right? So you have the acetamide parent name. 1-methyl group is N-methyl. If you had 2 methyl groups, you're following the same rules you always have. You're going to give both locants separated by a comma, and then you're going to put di, right? You're going to say that there are 2 methyl groups with your Greek prefix. Let's do an example. Say we have different R groups, and let's say we have multiple R groups. All right, so my parent in here, the longest continuous chain with that amide functional group is 1, 2, 3, 4, 5. So this is a pentanamide. And there are 4 methyl groups. You have 1, 2, 3, and 4. And then you also have, an ethyl group. Well, ethyl comes before methyl in the alphabet, right? E before M. So we have N-ethyl. And then I'm only going to write the word methyl once. So I'm going to put all the places it shows up. There's a methyl on N. There are 2 methyls on carbon 3. And there is a methyl on carbon 4. It is a tetramethyl compound. And then the parent is, of course, pentanamide. All right, so N-ethyl, N334, tetramethyl pentanamide. The last bit of nomenclature we're going to cover in Chapter 20 is nitriles. Nitriles are carbon triple bonded to a nitrogen. If this is the highest priority functional group, then you are going to drop ic acid. In fact, you're going to drop oic acid because what you're adding is O-nitrile. If you wound up having 2 O's in there, it wouldn't be the end of the world. So what you're going to see here, where people often make a mistake, is they don't count their carbons correctly. The carbon in the nitrile is the carbonyl carbon. So if you have 1, 2, right, that's based on acetic acid, it's acetonitrile. Benzoic acid becomes benzonitrile. Where it can get tough is when things are written like this. Oop, let's not turn you sideways. It's going to be 1, 2, 3, 4, 5, and 6. So this would be hexanonitrile. Now, for each of the functional groups we've learned so far, it's going to wind up being your highest priority functional group because I'm not showing how to name it as a substituent. There are ways to do that, but at some point we have to draw the line or we'll be learning nomenclature for years. The nitrile is a really easy one to name as a substituent, and it's really common. So If your nitrile is not the highest priority, you are going to call it a cyano group. So if we had something like, actually, well, we'll do a couple of examples here. Something you have to watch out for. And I want to do this one very specifically. Okay, and let's also do this practice problem. Okay, so in neither case is the nitrile the highest priority functional group. So the highest priority functional group for this top example would be 1, 2, 3, and 4. I have to cut it here because the carbon can't be in the substituent and in the parent. It can't work that way. So I have to make this cut here. So this is a 4 cyano butanoyl, right? Butanoic becomes butanoyl chloride. Down here, your carboxylic acid is your high priority. It is going to be a meta or 3 cyanobenzoic acid. I will give you a priority list moving forward when you have to do nomenclature. Keep in mind, you always need to find the highest priority functional group, and then everything else